Project. Select that one. Right. So, dear participants, welcome to the last day of the atal FTP session. Today morning session will be taken by me, Dr. Session-1, Associate Professor, Deputy Department, Finance Law, Institute of Technology and Science. Okay, so let us start the session. Today's session is on production order control design and for the electrical vehicles. So in this, we will have the different controller explanation, and then we will see the different papers, how to write the papers, and then discussion of the papers, paper session, article discussion. So all these things we will be seeing. So on the first day itself, we have seen that the controller design will be having a closed loop block diagram given by this. So here we will be having the reference, and then controller, and then plant P, controller C, plant P, and then output value Y, and error signal. This error signal is the difference of the output and the reference. And you will be having the disturbance at the output also. And this controller will generate a signal, control signal U based upon the error. Okay, this is the normal closed loop block diagram. So this also you can apply for the electrical vehicles, right? So here the plant will be the transfer function of the electrical vehicle, and the C will be any controller. Here we are considering the fraction order controller, and we have seen what is a fraction order controller. So in the equation at the bottom of the slide, it is given by the controller transfer function for the fraction order PID controller. Okay, so we will be having total 5 parameters based upon the fraction order controller configuration. You can have different number of parameters, but in this controller configuration, what we have considered, so the number of parameters is 5. So Kp proportional controller gain, Ki integral controller gain, and Kd differential controller gain, and then lambda the fraction order of the integrator, mu is the fraction order coefficient of power of the differentiator. The values of lambda and mu varies between 0 to 2 normally. So for stability reason, generally they are preferred 0 to 1, but you can have the values up to 2. So beyond 2, it is discouraged. It is discouraged to have values beyond 2. So you can have safety between the values between the 0 and 2. Any fraction order value, non-integer value. Sometimes it is also called as the non-integer controller. So the lambda values can be assumed 0.1, 0.15, 1.1, 1.5, 1.75, 1.99, like that. 2, you can have both integer and non-integer, not only always non-integer. It can have the integer values like 0, 1, 2 also, but preferably you will be having the non-integer values. So this transfer function definition and all we have seen. So different soft computing techniques we have seen. Okay. So this is a adaptive neural network. So fuzzy inference systems, adaptive neural fuzzy inference systems are artificial neural networks or fuzzy logic controller. They are used here for representing the controller, that is design of the controller, and they can be used for the identification and modeling of the system also. That means if your model, if your system is having a nonlinearity, it is difficult to represent with a mathematical model, right? So no, we have some techniques, but they are difficult to implement practically. So what we will do normally is generate a set of input and output values for the system, and use this set of input and output values for the modeling of the system, and replace the system, actual system, with the model of the obtained from the neural networks and fuzzy logic. So ANFIS is a combination of neural network and fuzzy logic, adaptive neuro fuzzy inference system. So it combines the advantages of neural networks and fuzzy logic. Fuzzy logic you already previous for 5 days the resource persons have discussed about the fuzzy logic. So it will be having fuzzification, defuzzification, fuzzy inference engine, a set of rules, if there rules, all these things will be there. So you will be having the fuzzy values, unlike the normal control where we have crisp values. Fuzzy values will be there, and different set of functions will be there for the fuzzification, like trapezoidal. All those functions will be there. And similarly, in the case of neural network, you can say that you can see that. So it is having the so this is the input layer, hidden layer, output layer, and we will be having the weights associated here, and here we will be having the weights associated. Number of hidden layers can be more than one also. Similarly, the input and output layers will be only one. One input layer, one output layer, and number of more than one hidden layers also there. So this is a simple configuration where we are having only one hidden layer. Okay, one hidden layer, and they will be having the sigmoid activation function, and then which is a nonlinear function. Then we will be by training the neural network, the weights of the neural network will be adjusted, and you will be having different configurations, radial basis function, sigmoid function, like that, and then we will be having feed forward network, back propagation algorithms to adjust the weights and strength of the neural network. So this is what normally it mimics the human brain. It mimics the human brain. Okay. So such system will be useful for representing the controller and identification. Okay. So if you take a electrical vehicle system where you will be having the AC/DC and DC/DC converters. Okay. So because your motor is a AC motor, like PMSM or induction motor, three-phase induction motor. Okay, but the storage battery is a DC. Okay, so there should be proper converter design in between the battery to the motor. So first of all, you will be having the DC-DC converter from the battery side. So you have to use bidirectional converter. Okay, well, charging the battery, you will be giving the current to the battery. Similarly, while taking the power supply from the battery, the current flows in the opposite direction. So this converter setup will be a bidirectional converter. So current flows in both the directions. We will be having the high frequency MOSFETs. Okay. So while charging, the supply the regenerative mode, you can give the supply from the generator. It will be having AC supply, then it is converted to DC rectified, and then we will be having a capacitor DC link. then it is converted to the proper voltage. So normally for the batteries you will be having battery bus in the electrical vehicles you will be having 200 volts. Then it is given to the batteries. Similarly, in the reverse direction, if you are giving a supply here to the motor, you will be having in the current will be flowing in the reverse direction. So instead of the neural networks, if you want to use fuzzy logic also, you can use this is a grid connected electrical vehicle, that is microgrid connected. So as our title indicates, so microgrids are normally giving supply, taking supply from the solar PV panels or windmills. Most of the cases in the highways, small wind turbines are used for the generation of the power. Similarly, if you are using the electrical vehicle in the town or city, so the normal houses, commercial buildings, or commercial hospitals or offices or educational institutes, they will be using the PV. PV will be the preferable choice. Okay. So you can install on the rooftop or on the elevations of the buildings. You can install the based upon the area available. You can install the PV panels. Okay. So the PV panels they will generate DC supply based upon the installation capacity, and that is using the power electronic equipment. You will be giving the power supply to the our electrical vehicles. So here also the power supply is two directional. That is so when from morning 9 to 5 the electrical vehicles will be sitting idle, right? So during this time these vehicles can give power supply to the batteries, right? So batteries and grid also. Charging the battery, local battery, energy storage, and then if you are using the proper inverters and LCL filters, so you can supply the power to the vehicle to the grid. So during the idle hours, when the vehicle is not running on the roads, when it is staying in the office 9 to 5, or when the vehicle is staying idle, you can charge and batteries and give the power supply to the grid. It is called as vehicle to grid. Okay, so you can set the state of charge controllers, and then based upon the state of charge, if the state of charge falls below the 70%, then from the grid it will take power supply. So this inverter acts as the rectifier, and power supply is given to the batteries. But in the batteries as well as the electrical vehicle. Okay, so you can install batteries external, and also you are already having the batteries in the electrical vehicles. Okay, now we are having different advanced controllers. These controllers will be already we have already discussed in the first day's Monday morning session. Okay, so this is the model reference adaptive controller, model predictive controller, machine learning methods, and then what are the applications. Okay, okay. Now we can see that here how the algorithms like GWA, Grable optimization algorithm, or Whale optimization algorithm, PSO particle swarm optimization algorithm, all the latest swarm intelligence based soft computing techniques you can use for the controller design. Okay, so here you are having the your PV panel installed capacity. MPPT algorithm will be used for the generating or extracting maximum power from the power PV panel, which will generate the possible modulation pulses, PWM pulses, and given to the converters. And we will be having a capacitor which will take care of the always power supply, even though sometimes power is not available due to the rectification methods. Then it is given to the DC grid. This is the microgrid available, DC local grid available, microgrid available in the building, whether it is house or commercial complex. Then it is given to the unidirectional DC-DC converter. Then it is given to the electrical vehicle for charging. So we have seen that various resource persons discussed that this EV charge controller is required for the maintenance of the state of health and state of charge, SOC and SOH. Okay, so this current and voltage values continuously from the electrical vehicle they are taken, and the health is monitored, and based upon that the voltage from the DC-DC converter is controlled. Okay. So here you are having the bidirectional converter, here you are having unidirectional converter. So the bidirectional converter, what it will do is it will charge the storage battery when excess power is available. Okay. Similarly, it will when the battery is fully charged, the power supply can be given to the DC microgrid, and it will be given to the electrical vehicles for charging. Okay. So when excess power is there, battery will be charged. When less power is there, battery will supply power to the electrical vehicles. Okay. So here we will be having the DC reference voltage here, and from the grid, what is the voltage available? Based upon that, the grid voltage is always maintained constant. So any difference is there, we will be having the error signal generated, right? So from that, you will be giving the error signal to the fraction order PI controller. This fraction order PI controller, it will use these controller parameters will be tuned with the help of the Gray-Wolf optimization algorithm, or any algorithm you can take. Soft computing techniques you can take, right? Okay. So these parameters will be tuned, and the controller will generate the signal, and based upon the controller signal, you will be having the pulse width modulation pulses are generated for controlling the converters. Okay, this is the common configuration followed in all the electrical vehicles. Now see, so if you take an electrical vehicle, the different controllers are required at different stages, right? So one stage is speed and torque control, another one is the DC-DC and AC-DC converters design, that controller. Okay, so different stages, different controllers are there. The electrical parameters like voltage, current, power you have to control. Mechanical parameters like torque and speed you have to control, right? So for different control systems, the transfer function needs to be changed. Right? So what we have seen earlier, this is a DC-DC converter and bidirectional and unidirectional used for the state of health and state of charge control. Right? So now, similarly, if you want to control the speed and torque, so this diagram you have to use. So this is your induction motor, three-phase induction motor, which is driving connected to the back axle of the your electrical vehicle. So this is the omega represents the angular speed. Okay. So here you are different methods like direct torque control you can use. Here this is the fraction order controller which we are normally proposing. Okay. So for the fraction order controller, it is taking the input speed, voltage, okay, and then torque, all those signals it will be generating. Okay, this is the mechanical part, this is the induction motor, this is the converters part. Okay, so this diagram represents the speed control techniques we have to use. Okay, so here you are having the advanced machine learning controllers like artificial intelligence controllers like adaptive neurophysical inference system, ANFIS system. Okay, this one is the ANFIS controller you are using for the fraction order purpose. So we have to tune the controller parameters, that is fraction order control parameters, artificial using the artificial intelligence. That artificial intelligence is obtained from the fuzzy logic and neural networks combined, that is called as the adaptive neurophysical inference sets. We will be having the different libraries in the MATLAB. We can simulate in the MATLAB also. Okay. So this is using an algorithm. So we can see that. So you will be having the objective function. This objective function normally you can have either time domain like parameters like steady state error, rise time, peak overshoot, settling time, all these parameters, time domain parameters, you can give a combination of the time domain performances. And you can give the frequency domain performance indexes like gain margin, phase margin, Okay, all these things, and you can combine both time domain and frequency domain in the single objective function. So all these things just you can add and give weight for each of the performance criteria. Suppose if I want to give more preference for the steady state error than phase margin, what I will do is I will multiply 10 or 20 with the steady state error, and I will multiply give weight single one only weight for the phase margin, like that. So based upon the change of the weights, you can give the more importance to different parameters. Okay, and you can have the combination of the parameters, both time and frequency, right? Perfect, nice. And then so each iteration it will be calculating the weights and objective function is calculated. Then it will check whether the maximum number of iterations is reached. If the maximum iterations is reached, it will stop the execution of the algorithm. Okay. If the number of iterations are still pending, then it will continue the algorithm and it will increase the count of the iterations. Then again it will calculate the parameters like gains and fractional order values, Kp, Ki, Kd values, lambda mu values. So here in this example, this example they have taken that the fractional order values of the integrator and differentiator they have taken between 0 to 1, okay, which is normally forward. Otherwise, you can take the values between 0 to 2 also, right? Depends upon your flexibility. What happens is if you are going beyond one values for the integrator, so it will lead to slight stability problems. Beyond 2 it is not completely unstable, but between 1 and 2 also, since you know that 1 by s square, 1 by s is integrator. 1 by itself, s itself is a integrator having the order of the system increased by 1. So if you are going beyond 1, the system order increases beyond 1, right? So system order will be increased by 2 if you are going up to 2. Like that, always the system order increase causes what? It will increase the stability problems because you are going the higher order system. Higher order systems are always prone to stability issues when compared to the lower order systems. So since controller and plant it is a closed loop system, the increase in the order of the controller obviously it will go for the increase in the overall closed loop system transfer function. Okay. So here this is a simple closed loop block diagram, not what normally we will do. And here this represents the MATLAB diagram. Okay. So here you can take that the fraction order controller will be having proportional, integral, differential gains. This lambda is the integrator order, mu is the differentiator order. So total 5 parameters are there. These 5 parameters in this particular example you are using the genetic algorithm. So this genetic algorithm is also a soft computing technique. So it will generate all the 5 controller parameters based upon the objective function. Here I am taking E as the error. So inside the inside the algorithm, I can modify the objective function. Okay, right. So you can see that the plant is replaced by the electrical vehicle. The plant is replaced by the electrical vehicle. Okay. So this control signal U, it will based upon the transfer function you have chosen, right? If it is speed control and torque control, one different transfer function is there, and you have to generate the signal based upon the transfer function U. Okay. Then if you take the battery and converter side, electrical part, you have to take different transfer function, right? Normally, even though the actual transfer functions will be higher order systems like the second order or third order, normally you will reduce the transfer function to the first order or first order plus time delay systems, so that the design of the controller will be easy. Okay. Different estimation techniques are there, approximation techniques are there for reducing the order of the system from the higher order to the lower order. Okay. So this is the MATLAB implementation. So these are the references what we have seen for the module discussion. So if you have any doubts till now, so I can take the questions. Then we will move to the different other methods of controller design using the soft computing technique. What are the different controllers? That part I will take here. Okay. So if there are no questions, I will proceed. So this block diagram, it will give a clear picture of what is happening in the controller design part, right? So you can see. So here I have taken one couple tank example. This you can replace with the electrical vehicle. So this is the system, normal system. So this is your controller, and this is the objective function what you are normally using. And this objective function will be given to an algorithm, and that algorithm will decide the controller parameters. Okay. So by it is called as the controller tuning. Controller tuning means what is meant by controller tuning? Can anybody tell? What is meant by controller tuning? Right? So yes. So it is nothing but obtaining the controller parameters based upon the objective function you are deciding. Right? So that means the time domain or frequency domain specifications are inserted in the objective function. That objective function is minimized by executing the algorithm number of times, and that will give the controller parameters. Okay. So here I have taken the objective function as integral square error, that is the integral of the square of the error. Similarly, you can take different controller objective functions. Okay. So now we will see because the title itself we are showing that advanced controllers for micro and electrical vehicles. So you will see the different advanced controllers. What are the controllers available? Advanced controllers available one by one. Their structures, how to tune the controller parameters. So what are the effects and results and all we will be seeing. Right. So here you can see that this is called as internal model controller. This is a controller that is proposed some 20 to 30 years back itself. So what it will do is it will take the model of the system without any unstable parameters. Okay. So normally if you take a system, it will have both unstable poles and stable poles. So 1 by s plus 1 into s minus 1 if you take a transfer function as an example. So 1 by s plus 1 is a stable pole because it lies in the left hand side. 1 by s minus 1 is a unstable pole because it is lying in the right hand side. Okay. So what it will do is in the modeling part, what we do, we will remove that unstable pole 1 by s minus 1 and we will take the model of the system. Okay. Okay. So we will remove that unstable part. Unstable part, and we will obtain a model G tilde. G tilde is the model of the system, right? So then you can this Q of S is called as the internal model control. So if you simplify this overall block diagram, you will get the controller C of S. That controller C of S will be having a transfer function of Q of S will minus Q of S into G of S. Here we are assuming that model of the system G tilde of S and transfer function of the system G of S are closely matching. Then only you can obtain this simplified version. Otherwise, it will be a complicated one. Okay. So what is the example here? The model of the system and the actual plant G of S, G tilde, G of S are similar or matching. Now, if I take a first order plus time delay system, even this transfer function I can use for the electrical vehicle, and I have used this in one of my implementations, and it worked fine. So I assume that the speed control of the electrical vehicle you can represent with a first order system. So even though the higher order system transfer functions are available, I will reduce that to a first order plus time delay system. It is a basic approximation techniques. So I will obtain the first order approximation of the system. Then I will use this model for the design of the controller. Okay. So now the FOIFC considered, that is the fraction order controller considered, is given by this transfer function 1 by 1 plus Kc into S4 alpha into Kc multiplied by 1 plus 1 by Ti of S. Here this part is the integer controller part, like it is a integer order PA controller, right? Normal PA controller. This part is the fractional part. So here this is a TC. TC is the time constant of the filter, and alpha is the fraction order between 0 to 1. So the first part 1 by 1 plus TC into S4 alpha is a fraction order filter, and the remaining part is the integer order PI controller, which we normally use in the industries from the long time. Okay, this is a popular PI controller, is a popular technique. Okay, then we will from this plot diagram we will calculate this error between the reference and difference between the input and output. Y of s and R of s, we will take the difference, that will give the error. Okay, right. So that error we will calculate. Then we will calculate the integral square error. So take the difference, find out the error, square the value of the error, and we will wait for a time. So 0 to t seconds I will wait, and how much this total value of the error is accumulating, square of the error. Okay, right? You are able to understand, right? So take the difference, find out the error, square the error, and square of the error we will wait for some time. It will accumulate. So E1 square, E2 square, like that it will keep on adding. So it will accumulate, right? So that accumulation we will take as integral square error. Okay. And then these are the equations concerning the particle swarm optimization algorithm. Particle swarm optimization algorithm, that is PSO algorithm you will call. So here we are having the basically global and local values, that is best values, particle best and global best, you can say. So we will have number of particles. That particles will be initially given some values, initialized to some values. Then they are allowed to explore the total space of the objective function. Then based upon the positions of the particles, the objective function is calculated at each iteration. Iteration based and total global based and local based we will be taking. Both again particle velocity and particle position are updated. That is, particle velocity is updated means it can move with a different velocity. It is allowed to move with a different velocity, and its position is also changed. Each iteration it will start from a different position and it will move with a different velocity. Like that, it is allowed to explore the entire area of the system. So you will be having the upper bound and lower bound, and based upon these bounds only it will search the area. So how many parameters, controller parameters are there? Every parameter you have to decide the lower bound and upper bound, and number of iterations you have to fix, because it will take, if you are taking more iterations, then it will take more time for the execution. Okay. So here W is the inertia weight, then C1, C2 are normally chosen between the values between the 0 to 2. Okay. Then GK is the global best position, particle best position are taken. The positions are updated using the equation xi of k plus 1 is equal to xi of k plus vi of k plus 1. That is the position operation. Next, velocity operation is vi of k plus 1 is equal to w into vi of k plus c1 into particle best minus existing position. Next, c2 into global best into minus xi of k. Okay. So C1, C2 represent some constant weights. We can determine normally they are taken between values will be 0 to 2. Okay. So this is the flowchart algorithm, step by step algorithm steps. What are the steps you are going to find out? The first step, obtain the model of the system. Okay. So this model you can either obtain a transfer function model or you can take the neural network model also, right? So if the system, that is our electrical vehicle system, if you are taking, it is having the nonlinearity included. If you want to take exact accurate model, okay, what you will do, you can take you can include the nonlinearities and you can take the to represent that nonlinear model, you can use the neural networks, right? Then select the upper and lower bounds of the controller parameters. Okay. Then construct the objective function. This objective function you are having choice. Right. You can have different objective functions based upon the time domain, frequency domain parameters, and our selection. This is completely objective function is completely our selection based upon our requirement. See, if I want the response, the controller response to be fast, I will take the settling time to be small value. I will give the settling time more preference. Correct? Similarly, if I don't want the peak output to exceed, then I will give more preference, more weight to the peak output, like that. Because in the real time, even though if you see in the autonomous vehicles without a driverless, without a driver, so the response time should be fast. Okay. So then in that case, I will take the setting time and rise time as the more preference values. Okay. Like that. Then choose the proper parameters of the algorithm. So algorithm parameters also I have to initialize. Okay. So that is how many iterations, 10 iterations or 20 or 30 iterations. How many iterations I want to execute the same algorithm. Then different what number of particles, 10 particles, 5 particles, 20 particles. How many? What is the size of the particles? That also I have to decide. These are all called as the parameters of the algorithm. Okay. Then obtain the control parameters after execution of the MATLAB code for the algorithm. Okay. I will write all these things, and there are two steps in the main and objective functions. Two functions will be there. So two functions I will take care of the changes, then execute the algorithm in the main function. Then it will take some time based upon the number of iterations and number of particles you have given. So maximum it will take some 10 to 15 minutes. Okay. If I'm talking about the particles form optimization. So if you will see that we will go in the next slides. We will go to different algorithms also. Some of the algorithms they take less time for the execution. But for the case of particles form optimization, the execution time is less. Okay. Execution time is more. And then simulate the controller using Simulink and check the step response of the closed loop system. Okay, that means from the after execution we will get the controller parameters, right? The kpk, kd, lambda, mu, or in the previous example we have seen, right? Previous example. So here, this is a different controller. So here the number of parameters is tau c, alpha, kc, ta. That is 4 parameters are there. If you take a FOPID controller, you will be having the 5 parameters. Here I am having the 4 parameters. That is based upon the choice of the controller, the number of parameters will be varying, right? So all these parameters will be obtained after the execution. After algorithm execution is over, you will obtain the parameter values, controller parameter values. That is called the tuning. That is tuning is done by the soft computing techniques like particle form optimization and all those algorithm values. Algorithm use the controller parameter values. Okay. Right. So here you can in this table you can see that what are the parameters of the algorithm I have taken. Swarm size is taken as 5. C1, C2 values are taken as 0.9 and 0.4. C1, C2 are taken as 2. Number of iterations are taken as 10. Now this represents the flowchart of the total algorithm. Okay, so initialize the parameters, initialize the controller parameter. This is a PSO algorithm, this is controller. Both you have to initialize. Then evaluate the objective function at each step. Okay. Then set the iteration count, increase the iteration count to k is equal to 1. Then update the controller parameters. Okay. So initially we will take one controller parameters, that is the initialization. After first execution, these parameters will be updated. Controller parameters will be updated. Then you will evaluate the objective function based upon the current iteration. Then you will check the objective function, and like that, next you will increase the increment of the execution count. Then whether the k max is reached. That is, if you are choosing iterations as 10, k max is 10, right? So the maximum iterations is 10. So that is, you have to repeat the algorithm. You have to repeat the algorithm 10 times. Repeat the algorithm 10 times. So after the first execution, one iteration is over. After the second iteration, k is equal to 2. After the third iteration, k is equal to 3. Like that, keep on the iteration count keep on increasing. So after all the iterations are over, the k max is equal to 10 is reached. We have to stop the execution of the algorithm. Then, print the values of the controller parameters. And what we will do is we will take these controller parameters, take a Simulink file, keep the values of the controller parameters, keep our keep the transfer function of the our alternate vehicle parameters, then execute the Simulink file, then it will give the output. So you see, check the values of the plot, and then if the plot is not satisfactory, okay, that is, if you take different, you can give some tracking values, right? So some road pattern you will give, then check the pattern. If the pattern is not satisfactory, then what you will do, you will again go back to the, you will come back to the execution part here. You will come back to the execution part. You will change the objective function, or you will change the parameters of the initialize the parameters of the algorithm, then change some modifications to the lower bound and upper bound of the controller parameters. That means this what is the bound you have selected, lower bound to upper bound. It is not fitting. It is not useful, right? So then what you will do? You have to either reduce the bound or increase the bound. And if you are increasing the bound, what it means? The controller parameters I am allowing to vary up to a higher level. Suppose if I allow the kp from 0 to 5, okay, the lower bound is 0, upper bound is 5. Okay, I am allowing kp to vary between 0 and 5. Similarly, ki between 0 and 1. kd is between 0 and 10 or 20, like that. So, if these bounds are not suitable, it will not give proper performance of the system. Then what I have to do? I have to change the bounds. Either reduce or increase. If I am reducing, initially it is the bound is between 0 to 10. I am reducing the bound from 10 to 5 now. Okay. I am allowing only kp value to vary between 0 and 5. Okay. So like that. If I am increasing, similarly, I am changing from 10 to 20. So I am allowing kp value to vary between 0 to 20. Like that, I have to change. I have to do analysis based upon my requirement, right? So you know normally that a PID controller, if you take proportional controller, it will increase the rise, it will reduce the rise time. Integral controller, it will reduce the steady state error, right? So Next, derivative control, if you take, it will reduce the peak overshoot. Okay, integral control affects the steady state performance. Derivative controller, it will affect the steady state transient performance. Derivative control affects the transient performance. Integral controller improves the steady state performance. So based upon the requirement of our system, right? So if I want the electrical vehicle to go fast, I will reduce the rise time. That means I want to increase the KP value. Similarly, if I want to make our electrical vehicle to have zero steady state error, so I have to more focus. I have to give more focus for the integral controller. Like that, based upon our requirement, actual real time requirement, I will adjust this KPK, KD, lower bound and upper bound. Okay. Then again, after making the changes to the lower bound and upper bound of the controller parameters, I will execute the algorithm one more time. That means some 20 iterations or 10 iterations I will take. Okay. And then again I will obtain the controller parameters. Now the new set of controller parameters that I will take, I will again do the Simulink execution, then check the performance. If the performance is not found to be suitable, now what I will do? I will stop the execution. Then I will use that controller parameters and I will update the values. Okay. So you can see based upon the executions, that is the number of iterations. Here I have given the number of iterations as 10. K max is equal to 10, right? So 10 iterations it will keep on executing the, every time it will find the objective function and then it will obtain the controller parameters. So you can see that after beyond 3 it has stabilized. So there is no use going beyond more than 5. Okay. So you can see that even though if you make changes to the your PSO algorithm parameters, it has already settled. Okay. So the objective function gradually it is reducing. So if your algorithm is good, it will settle within a less number of iterations. If your algorithm choice is not good, then it will take more number of iterations to obtain the control parameters. Okay. So this is a verification of your check on the control parameters for the algorithm. Okay. So this is my system. So based upon the transfer function, I have obtained the controller like this. Similarly, you can execute same methods. You can execute for the electrical vehicles. You can take and use this algorithm. I will share the algorithm in the WhatsApp group we have created. Or if I want to send you to my personal mails, I will also send the details of the algorithm and plan how to execute and all. I will share. Okay. So like that we go. So these are the execution results. So here you can see that clearly the set point I have given as 10 centimeters for the tank. So these are the responses for the different controllers. Like this is the proposed fraction order controller. Next, the integer order controller I have taken. Then again one more reference I have taken as FOPAD. Okay. So FOPAD is fraction order PID controller, FOIMC is fraction order internal model controller, IOPI is integer order PI controller. So three controllers I have taken for the performance comparison. And these are the results of the step response. So similarly you can use for the speed control or state of charge control, you can use for the electrical vehicles. So from this performance you can see that which is better, the red line is better because it is not having any overshoot, peak overshoot, it is settling fast. Okay, it is settling fast. Then steady state error is also zero. So a lot of things you can observe. Okay, the better performance you can check with the help of all these controller parameters. So the left hand side is the simulation results and this right hand side is the experimental results. and this is the bottom part is the control effort. That means what is the strength of the control signal U? Okay, what is the strength of the control signal U? So initially you can see that the control signal is more, then gradually it will, once the error settles, less control action is required. Okay. So from the comparison of the experimental and theoretical results, you can say that they are validated and matching. Okay. So this is a comparison of the different controllers parameters. So for the controller performance comparison, normally what you will do is you will take different parameters, not only the rise time, settling time. There are some integral time performance indices. There are integral time performance indices. They are called as the ISE integral square error, IAE integral absolute error, and then integral time absolute error, and then integral time squared error. Okay, these are all the calculated and they will be compared. So whichever control is having less values of these performance indices, it is said to be, that controller is said to be good. Its performance giving good performance when compared to other controllers. Okay, for if you take IAE integral absolute error, so 4.24 into 10 to the power of 3, 8.7 into 10 to the power of 3, 4.36 into 10 to the power of 3. So if we compare these three controllers for the parameter IAE, so which one is giving the least value of the IAE? Yes, tell me. Which one is giving? Yes, FOMC is giving the least value. So 4.24. So that means it is having the less value of the integral absolute error. Okay. So it is found to be, our proposed control is found to be good. Similarly, you can calculate rise time, settling time, peak overshoot, steady state error. All those values you can calculate. So if you take the peak overshoot, you can see that our proposed control is giving only 2. That is 2%. Peak overshoot means the steady state value minus peak value by steady state value. So you will multiply by 100. So percentage value we will take. Okay. So you can see that other controllers are having the peak overshoot, higher peak overshoots, right? Our proposed control is having only less peak overshoot. Okay. Then so for the experimental also I have compared. Okay. Peak overshooting is more means it will suppose if you take electrical vehicle, if your peak overshoot is more, the vibrations are more, right? So beyond the peak value it is giving, and it will sometimes it will damage the our electrical equipment and mechanical equipment also, because of this more peak value it will damage the physical values. Okay. Okay. So another one more controller I have one more controller I have proposed. This is a higher order controller. This is a higher order controller. Okay. So here I have taken the controller transfer function. This is the lower filter. Okay. This is the lower order filter. Then one more system I have taken. This part will skip. Okay, right. So this is a higher order control. That means the filter initially we have seen that it is only 1 by 1 plus tau c into S4 alpha. Okay, that I have taken one more term. That is the filter is having higher order. Instead of just a first order, I am having a higher order. Square term. Square term is two filter terms are there. So order of the filter increases. Order of the filter increases. and this is the integer part, this is the fraction order part. So integer part, earlier we have taken kb plus ki by s only simply. Now I have included the derivative term also, and here I have taken the second order filter. Okay, so the filter is having two values, two terms. Now the amplitude function taken here, I have included. You can see that peak overshoot, setting time, and integral square error. This is ISE. ISE, setting time, peak overshoot. All the terms I have included. This is only for the time domain performance improvement. Okay. Yes. Yes, that we are going to see. Okay. The results will be shown. Okay. So you can see that I have given more importance to the peak overshoot. How I am giving more importance? By multiplying it with 10. So more importance is given to the peak overshoot, then to setting time, then to ISC. So if I include this with multiplied with 10, then these two are given equal importance. Like that you can give a choice. Okay, based upon my requirement, I can give more importance. That is weight, more weight. More importance means more weight. If the multiplication factor is high, that will be in the objective function that is given more importance. Like that. So this is the comparison of the results. You can see that. So this is FOIMC with lower order filter. Reference 1 lower order filter. That is our previous controller we have seen. Now I have increased the order of the filter. Okay, higher order filter. So this is first order filter, second order filter. So you can see what is the improvement of the performance. As you asked, what is the improvement in the performance? So clearly it indicates green one is your reference to, that is FOPA only without any higher order filter. Okay, reference one is blue color. It is having more peak overshoot. Next, red color is the higher order filter. Okay, so you can clearly see the comparison of the results, which indicates that the red one is having no peak overshoot. So you see, this is the steady state value. From the steady state value, it increased to this value. Okay, so from steady state, this much of increment is there up to probably it increased. Okay, so this you can extend for the electrical vehicles, like the speed I am giving, reference speed I am giving 1500 RPM I am giving, let us say. Okay, so if we are using the reference one, it is speed is going beyond 1500. Now if I am taking the proposed controller which is not exceeding the reference value, the peak value increment beyond the reference value is small. That's why our higher order filter is good. Okay. So this is the comparison of the three controllers. Here in this example, if you observe, all the controllers are fraction order controllers only. All the controllers are fraction order controllers only. So fraction order PA controller, fraction order IMC controller with lower order filter, fraction order IMC controller with higher order filter. And again, among the fraction order controllers also, you can observe clearly that higher order filter is giving the better performance, and these are the simulation results and these are the experimental results. Experiment means you will be having the system, right? So physical system. Yes, I will show the diagram. So this is the experimental system. So here we will be having two tanks will be there. Two tanks, tank 1, tank 2. So tank 1, the input I will give some water. Then what will happen? The water falls and gradually the level of the tank increases. Now from tank 1 to tank 2 you have pipe. See here, this is a pipe. So when tank 1 fills, some of the water goes to the tank 2. So tank 2 also starts to rise. Okay. So like this. So So this you can see in the case of chemical industries like paper industries, number of stages will be there. Process control industries, right? That algorithm is there. So now my simulink diagram is there. Simulation I have used. This simulation I have connected to a data acquisition card, DAQ card. The control signal will be given to this digital values. This DAQ, what it will do? You will be having a analog to analog digital to analog converter DAC. So all these digital values they will convert analog values. So it will generate the current signals, and the current signals are given to this board. This will send voltage to the motor. That motor it will open a valve, okay, and that valve it will increase the flow rate to the tank like that. If you want to close the valve, the less water will come to the first tank. If you open the valve, more water will come to the first tank like that. Based upon the control signal it is generating, that valve will be opened or closed. Okay, valve will be opened or closed like that. This is one experimental system I have taken. Huh? That means you are controlling the tag 2 level of the tag.